Hello everyone and welcome to our discussion of shear turbulence. We're working our way through locations where you find shear turbulence. And we already had a video on jet streams. We talked about the theory of jet streams. We looked at cross sections of the atmosphere, talked about upper fronts and the tropopause and locations where you find clear air turbulence. Now we're going to discuss flight planning. So when you're looking for clear air turbulence, you're looking at high altitudes. So you're looking at the upper level charts. And the jet stream, at least the polar jet stream, is usually focused at about 30,000 feet. 30,000 feet gives you about 300 millibars. So we're going to look at constant pressure charts. We'll start out at 300 millibars or 30,000 feet, and then we'll work our way up. And what we're looking for is strong shear in these regions of upper fronts and also in the tropopause.
Here's a 300 millibar chart, and on this chart you can see red indicates the jet stream core, and in fact that's a jet streak, and you can see that the winds are moving along in excess of 125 knots. Now this is located over Oklahoma, that area of red. Notice how the winds there are about 125 to 130 knots, and by the time you get to Nebraska, the winds are only 10 knots in North Platte, Nebraska. So there's a very rapid change in wind speed on the north side of the jet stream, and that is where you're going to find the clear air turbulence in the upper front. As you go up through the atmosphere, the shear still looks the same. It looks like a very strong shear horizontally. And then finally, here we are 200 millibars, and this is where we're starting to get into the stratosphere. And the northern part of our map up in Canada and North Dakota and South Dakota is in the stratosphere, while the portions across Texas and Oklahoma are in the tropopause below the or in the troposphere below the tropopause. So the strongest shear is on the north side, the polar side of the jet stream, and that's where you'll find the strong turbulence.
There are some numbers that you should know that are from the Aviation Weather Handbook. Also, they're from the old Advisory Circular 00-30C, which deals with turbulence avoidance. And those numbers are, well, the first one is threshold wind speed. Whenever the jet stream exceeds 110 knots, then you can expect significant clear air turbulence. So looking for the maximum wind in a jet streak, if that's more than 110 knots, you should start to expect turbulence. Another number that you should know is the vertical shear gradient. If the wind exceeds more than 5 knots per 1,000 feet as you climb through the atmosphere, you can expect moderate turbulence. And what that means is, if you look at the example here, the lower level winds are 100 knots, the upper level winds are 125. If the difference in altitude is 5,000 feet, well then the difference 25 divided by 5,000 gives you 5 knots per 1,000 feet. And you can start to expect moderate turbulence when you see a shear that is similar to this. Another number that you should know is the horizontal shear gradient. If you have winds that are changing by more than 40 knots over 150 nautical miles, you can expect moderate turbulence. In this example that you see, the winds over North Dakota are 100 knots. Down across South Dakota and Nebraska, the winds are 190 knots. The difference between that is 90 knots. If that distance is 300 miles, you can set up a ratio, and 90 divided by 300 is equal to 45 divided by 150. So in this case, you have winds that are greater than 40 knots. It's 45 knots in this example, and you could probably expect moderate turbulence as a result of that shear.
So when you're planning a flight at high altitude and you're concerned about clear air turbulence, what do you look at? Well, first off, you look at the high-level significant weather prognostic chart. The high-level significant weather prognostic chart has areas of clear air turbulence. They forecast moderate to severe clear air turbulence, and they highlight those areas. Notice how these areas are very close to jet streams and typically on the north side of the jet stream axis. Also, you should look at pilot reports. Whenever someone's checking in, they're always telling the ATSC controller what kind of ride they're getting. Another thing to be wary of is that if you see pilot reports of wave activity, then you know that clear air turbulence is a possibility. Wave is the precursor to eddies forming and the formation of clear air turbulence, as we saw in the video before. Also, SIGMETs are put out, and also AirMETs are put out for high altitude turbulence, so check your in-flight advisories. And then also, if you go to the satellite imagery, you can actually see wave clouds forming in the jet stream, and those waves are perpendicular. Those clouds are kind of lined perpendicular to the jet stream winds. It indicates wave activity. And as we mentioned, that's probably the first indication at high altitude that of the onset of clear air turbulence is this wave activity. Here's a couple examples. Here's a jet stream. This one's oriented a little bit different. It's going from the south to the north across upstate New York. And you can see in northern New York little bands, and those bands are actually wave clouds, and those wave clouds are producing clear air turbulence at high altitudes. Here's another image a little bit closer of banded clouds. These are clouds. In this case, these wave clouds are formed in the jet stream, across the jet stream. In this case, the winds are moving from the west to the east across this image. If you want to look at more imagery from these clouds or from satellites, you can go out to this website, and they will show you cases of clear air turbulence and satellite imagery.
Next, we'll talk about how to fly clear air turbulence in the jet stream.
Other things to be concerned with when you're flying at high altitudes, you don't want to overstress the aircraft, so you want to perhaps reduce the aircraft to recommended turbulent penetration speed. Also, you should know that as you increase your altitude, your low speed buffet, in other words stall speed, increases with altitude, and your high speed buffet, in other words your critical Mach number, actually decreases with altitude. So they converge at your maximum altitude. You can see that as you get higher and higher, your operating airspeeds, the airspeeds at which you can maintain cruise flight, get smaller and smaller. There's a smaller range because at the low end you've got stall, and at the high end you've got high speed upset due to exceeding the critical Mach number. So the problem is that if you encounter turbulence at high altitude, it's very easy to exceed any one of these airspeeds if your operating airspeed range is very, very narrow, what we call coffin corner. So if you do experience clear air turbulence at high altitudes, typically a change of altitudes of 2,000 feet should give you a smoother ride. And if you're flying in different parts of the jet stream, if you're flying in well, not the jet stream, but around the jet stream, if you're flying in the tropopause, you might want to descend into the jet stream core to maximize your tailwind, or you might want to climb to minimize your headwind. Same thing with the upper front. If you're down in the upper front experiencing turbulence, the rule of thumb is to maximize your tailwind and minimize your headwind. Now, the key point here is that within the jet stream core, there is really no turbulence. It's in the sheared portions on the north side, and then also above and below the jet stream core is where you find the turbulence. But in the core itself, the ride is smooth. So if you can maintain, if you can stay in the core with the tailwind, then you'll get to your destination faster and you'll have a smooth ride. That's all I have for you today. Next time we'll talk about mechanical